Okay, so I'm very happy to welcome all of you and to welcome our speaker, Professor Deepak Nair. He is from ISC Hero Neuroscience Department, and he did his masters at IIT Chennai, uh, and followed by his PhD at Leibniz Institute of Neurobiology. So now you know that he's going to talk about super resolution techniques in neurobiology, and he did his postdoc at Interdisciplinary Center of Neurobiology, Bordeaux, France. And since last I think 8 or 10 years, he has been here, and he has a very wonderful lab and working at the frontiers, and where he's developing new microscopic techniques, super resolution localization microscopic techniques for neurobiology applications. And today he's going to talk about neuromorphic camera, a new kind of camera, also called event cameras for super resolution localization microscopy and its application in neurobiology, neuroscience. Okay, so now I welcome Professor Deepak. Please take over.
Yeah, I am extremely grateful to Partho and this wonderful initiative that he's creating. I mean, um, I think now it's a time that almost all of us or majority of us can get a lot of information from, like, say, internet and resources. So those people who are, who really want to get information, it is easier. But what is harder is to really see this information, or see the information that you gather in action, especially like high-end techniques like microscopy or superconductivity or magnetism or cell biological techniques. This all requires some, amazing person opening up the lab for you and letting you come and see that. That takes a tremendous time of energy, effort, and coordination. So rather than, I being thankful, I would like to thank Partho for doing this. And I'm just, happy to be part of it, to do my little bit, so that, so that we can have a good discussion in the next 1 hour or so. So, we started our lab at Center for Neuroscience around 2014, beginning of 2014. So Center for Neuroscience is one of the, recently established centers. It's not even 15 or 16 years that it has been established. So it's barely 15. So compared to the overall age of IAC, it's much more of a younger department. We are not major yet. So it's still 3 more years to be 18. And in 2014, we started our lab at Center for Neuroscience, which was like at the interface of trying to use high-end microscopy to study synapses. Though the prime aim of our lab is to study synapses, today I will try to stick to the methodologies, and I'll try to keep it simple, so that, I think simple. I hope, if any of you have any issues, just please stop me and ask. If I will try to give the best of my explanation. If not, Partho is here. He's always there to explain stuff. So now, coming back, so this is the lab right now, and this is the recent composition of the lab that we have. So whatever I am going to present here, I'm just a spokesperson for my lab, and without these guys, I wouldn't be here. So I'm more than any funding agencies and, any other facilities that is given to me. I'm grateful to these guys who have been we have been a team through thick and thin. There have been several hard times like Corona, lack of grants, difficulties in getting infrastructures, but all of them stuck, and their efforts is now paying off. So because every generation of students leave, the lab goes a little bit higher. It's at least a nanometer higher, and which is why I want to start by thanking all these guys. So now, as I discussed, the research at our lab actually discuss the biology at nanoscale. So that is life in and around 1 to 100 nanometer spatial scales. So we'll come to why 1 to 100 nanometer spatial scales, but it's a very interesting field where, like, different disciplines converge. I mean, it's not only about biology, but about, chemistry, physics, engineering, computational techniques, all merging from different angles to study how the self-organization, or it's okay, how the self-organization of things happen, or how just, I mean, just asking a simple question, because when I am trying to give you a question, or when I am trying to give you a task, there is always a deterministic response from your side. Understand? That is like you either do it or not do it. But if you look at the cellular level and the molecular scales that you are going to look at, there is enough stochasticity that means like it's not going to be that straightforward, because there is a lot of dependence on the concentration, lot of dependence on the time at which these molecules are in one place, at the time, the states of the molecules. So there is a lot of uh, things that happen at the molecular level. But somehow, if you look at the level of an organism, or if you look at some of the disease, you have a deterministic response. So our lab really tries to understand how the stochasticity at the molecular level eventually contribute towards like diseases, or things like, things like learning, memory, and all of this. So today I will be trying to take a small snippet of our study that has been recently published. So where we have tried to use non-conventional detectors to try and understand single particle localization. So now I hope, I do not know which background all of you guys are from. So biology, physics, chemistry, how are you distributed? Physics, chemistry background. So you saw the system already, right? So you know something about localization, nanoscale, spectroscopy, microscopy, and everything. So I think so. We will go straight in. So why we want to do it is, I have a pointer. I can use a pointer. No, I can use a pointer here. So basically, if you are trying to look at, if you are going to look at a behavior of an organism, you can see that the information in biology is spread across like more than 6 to 7 orders of scales. You understood? So you have, on one hand, you have molecules which are at nanometers, angstrom scales, and on another hand, you have behavior, that is like how we interact with environment, that happens at centimeter to meter scales. Understand? So there is a lot of nodes that is linking back and forth these linking back and forth these I can also use the hand to be like this. Oh, here is a laser pointer, right? So you have all of these different sizes. There's all of these different nodes that is interconnected to give you something that we see on a day-to-day basis. But I won't be going to discuss, I will not go on to discuss that. I will rather jump straight into the need of why. I've told you the reason why, because you have molecules which are hard to see, so you need to study these molecules at their individual environments. So why do we do? So for example, if you use a naked eye, just our eye, it gives us a resolution of around a millimeter scale. And like if you are trying to come down, you will see that, first microscopes were originally described in the early or late 1500s, and it had just 9 times magnification than our eye. And as time went on, there were microscopes were made which were like given resolutions or ability to see structures which are 200 times better than the eye. And as went on, there were like even Hooke's experiment where he tried to understand not only about just looking at the things, but also the movement of these things inside aqueous media or in a solution. For example, this is a bit gross to say, in this experiment that you see over here, what Leeuwenhoek actually did is that he tried to take the plaques that you have in your teeth and then try to mix in an aqueous solution and try to put it under microscope. What he saw was that, you saw this small cell at that time, he tried to define it as animalcules, and they were trying to move in all possible directions. And he tried to make sure from, the study says that from 2 women and 2 people who have never brushed their teeth. Don't say that, And he tried to see that, so which he tried to come back and say that it's not only about shapes, but also it's about movement that's happening in it. So eventually, microscopy then evolved to understand 2 things: to study how and where the molecules are localized, and on the other hand, how and when or from where they are coming in. So that is localization and trafficking. Understood? So, and again, to understand this further, compound microscopes were made, and and in late, or let's say mid 1800s, the physical theories or physical laws were further refined, and the Ernst Abbe came and said that, okay, how much ever you improve the optical system, there is a limit to which you can see things, beyond which you can't see. So we will try to understand what he said. He said that this is actually defined by the wavelength which you try to look at it. So for example, lambda, and the ability of your optical system to capture the light. Understood? So the more you capture the light, you get a better resolution. So that became, a mantra for science in the early stage. However, they wanted to capture the maximum light as possible. Now we will just look carefully what happens. So in a light microscope, in a regular light microscope, that means the microscopes that use visible light, for example, from 400 to 600 nanometer to excite the samples, your resolution is somewhere around 250 nanometer axially, that is laterally, and around 600 nanometer axially. So now, but if you look at, that part, the majority of the organizational substructures that is remaining here are below this limit. Understood? That means if you want to study, or if you want to observe the system using molecular resolution, it's not possible using conventional light microscope. So what did people try to do? For example, this is what I mean by it. For example, this is a cell where you have stained a protein called as a microtubule. That is like, that allows transport of material from one side of the cell to the other side, just like the highways and railways that we have. So they take the cargo and transport in a directional manner to a place. But if you are trying to zoom in, how much ever we want using the optical system that we have, you are not going to see anything but a pixelated image. Okay, you are not going to really see, and this is actually limited by your optical system. Now, if you look further, I mean, what does it mean? What does he say? This is a very interesting structure, is at a German city called Jena, and this is dedicated to Ernst Abbe, who actually formed the first physical laws of diffraction. And what Ernst Abbe has said is that the resolution of microscope is inversely dependent on its aperture. That means the more you can gather light, the better you can improve the resolution. The other option is that you reduce the wavelength of the light. But unfortunately, we can't do that, because as you reduce the wavelength further and further, this is not biologically viable. I mean, solution. And if you want to especially look at light. Second thing, if you look carefully, what he has said is that you cannot resolve 2 objects when they are closer than a diffraction limit. That means if they are far, you can understand. But if they are closer, if they are very close, you just cannot. So what people try to do again is to try and understand what really happens at a microscope. So if you have a very small object, if a microscope focus towards, this is a XZ direction. Okay, so you see that you have a lateral resolution of around 200 nanometers, an axial resolution between 500 and 600 nanometers. That it looks like a rugby ball in a way. So if you look at how the microscope or any lens system transfers a point object or a small light source, which is very, very small, you are always going to get a rugby ball like structure. Okay, and we can say that the center of the molecule is somewhere inside this rugby. Okay, so now again, we come to this. I just will put this equation so that you will constantly get reminded of this equation. But what really happens is something like this. So it's not a, when I say it's a rugby ball, it's not a uniform structure that you see. So when a point source like here is focused by a microscope, it forms these concentric circular patterns. These are called airy discs. Okay. Now, if I am trying to draw a line, like say, like this, like, parallel to this structure, or, and if you measure the intensity, you will see that more than 80% of the intensity is localized to the central zone. It's called the airy disk. And this is how the point spread functions actually look in 3D, these are the ripples, and you see like majority of the information is actually in the central zone. But what really happens in biology, or in any kind of, under any kinds of microscope, is very simple. So if the molecule is very far and you can actually identify individual centers, you can call them resolved. If they are super close, that you can't really calculate individual centers with a good precision, you can say it's unresolved. And if they are like just about you can calculate, you will say it is resolved, resolution limit. But this happens when the molecules are very sparse. Understood? But in reality, if you are trying to mix, a dye in an aqueous solution, or if you are trying to look at any cells or any fluorescent samples, you are not going to have the sparsity. What you are going to have is that all of these functions are going to merge, and you are going to get a big, large blob. Understood? So people for a century try to understand, how can we try to resolve these substructures, I mean these molecules, with the best of ability that they can. And it has resulted in a series of techniques which actually relied on improving the quality of acquisition. The simple mantra: more light, somehow more light. Understood? So they had, you had confocal microscopes which came in 97. You have near field scanning, you have multiphoton, but all of them, how much ever they tried, they somehow hit the limit, what Abhay has originally proposed to be. They can improve, they can somehow bypass, but they always go back and hit this one. So now these are different modalities that you see. They have tried to collect light by putting a pinhole. They have tried to see light, collect more light by putting additional objectives, so that you collect from all possible angles. Then you collect by trying to interfere them and get that one. But none of them actually worked. But then in 2014, for like the 20 years of their efforts in science, these people were awarded Nobel Prize, that they somehow circumvented this limit. Okay. And how they did is very simple, because they identified that the trick was not to focus on the optical system as such, but the trick was to focus on the molecules that you are imaging. So rather than looking at the optics, they started playing with the chemistry of the dyes that you have. And this is very beautiful, because Abbay's limit is a fundamental limit that is imposed in the laws of physics, right? But these people got the Nobel Prize in chemistry. Understood? But the reason why they got this was that rather than trying to play around the systems, they tried to go around and start playing with the chemical properties of the fluorescent molecule. Okay, so, and in the original papers of this, depicting the first physical principles, came in the time between 2000 and 2008. And 2008, Nature publications, they actually identified this as a method of the year that was going to change how we view science in the next 10, 20 years. And trust me, it has happened. So in the last 12, 13 years, there has been tremendous improvement in how we observe things, how we view things, that this has actually changed the way we see or we study biology, material science, sometimes chemistry, chemical engineering. A lot of applications it has been used. So what does it say? So now you can have two ways of trying to break this diffraction barrier. So majority of the talk will focus on the second one, but I'll give you a glimpse of what does it mean by a first one. The first one, we call it as a deterministic way, or the physicists would call it as now deterministic, is an ensemble fluorescence. So what's an ensemble fluorescence? Can anyone tell me what's an ensemble fluorescence? What does it mean by ensemble? Feel free. So what you have is that you have a collection of materials, a collection of molecules, or a collection of anything that becomes an ensemble. That means in the deterministic form of breaking the diffraction limit, you are actually recording the light from a lot of molecules. On the other hand, you also have stochastic, which means that you can break the diffraction limit by looking at the individual fluorescent molecules that is available. Okay. Now in the ensemble way, the original, idea was actually taken from our old, you can't surpass Einstein. He comes everywhere, puts his head everywhere. In this one also he did that. And you can see that originally he had discussed something called as Einstrahlung, which is also called as induced radiation. Actually, more and more when we went on, we tried to see the stimulated emissions. So it became a base of stimulated emissions. And like in early 90s, 94, Helen Wichmann actually tried to propose a model for breaking diffraction limit by using the stimulated emission. And in around, I think 2000, he actually showed this in practice. How they did is very simple. Again, the concepts underlying this kind of simple, but it's about how we put it in a lab, how we put it in a microscope, and how we bring all the things together. That is the hardest part. So conceptually, it is simple, because what you are left with is that you have a dye that can get excited, which you can see here. On the green side, you have the excitation spectra. And on the pink, right? Yeah, you have the emission spectra, which is the fluorescence. So what if you are trying to induce stimulated emissions? What happens is that you can quench, or you can make sure that all the molecules that are in the excited state can quickly come back to the ground state. Very simple. It's also the principles maybe many of you have studied, lasers, right? In a way, it's population inversion they try to do. So it comes in a very similar manner. It's not a principle of laser, but you can take the how will I say, the mojo from this one. Okay, so what they did here is very, very straightforward. So you have diffraction limited microscopy. So this is a regular confocal. What you do is that you have a microscope, it focuses the light. So you have a large, so this is like you're trying to illuminate a volume. So you can say that, okay, now I got my point spread function, and I can say that 250, my center of my fluorescence emission is somewhere in this 250 nanometer radius. Understood? So if we can somehow limit the centers, you have a better way of trying to understand where we can localize better. You can actually predict with a better precision where your fluorescence is coming from. For that, what they did is that they had a beam just like a confocal, and then they tried to have a second beam, which should be like, in the wavelength. So you see this red light, right, in the same. So what happens is that, so they have an annulus, like a donut like structure, and they kind of shine both of them together. Okay, so what happens now is that wherever you have the red beam, the fluorescence suddenly goes to the dark state. So you are left only with a small center. Okay, so suddenly you have from 250 to 300 nanometer, you have around 50 to your ability to calculate the center of emission is now located in a 50 nanometer radius, so that you have a better precision or better understanding of from where the molecular fluorescence or the fluorescence actually originates. Now, how can this is very interesting, because so there are several techniques that I have told you using different optical systems that has actually surpassed super resolution methods. Okay, so surpass the way of looking just below the diffraction limit. But when you say super resolution methods, what it tries to tell us is that it has an unlimited power of improving the resolution. For example, like if you are trying to I mean, just a simple example, our boss used to tell us, or our, is the idea of superheroes, right? So you can give any amount of a particular stress, maybe Superman for strength. I mean, same with Hanuman, you strength. And if you are each of them comes with different kind of powers, whom it can be, kind of it extended infinitely, so that way it is going to go to the minutest possible. And in case of super resolution, super conductivity, all super kind of methods is going to the best way possible without a limit. Okay, in this case, the limit is actually imposed by the ability to quench the external fluorescence. The more you can quench the fluorescence, the more you can actually, with better precision, you can actually calculate the centers. Okay, and so this is called super resolution method, and they have modified this equation. So the more this eye saturation is, you will have a direct effect on its on the final resolution that you have. So now what did they do? So for example, here you have let's say a regular light microscopy image on below this dashed line, and a super resolved or a stud image on the right side. What is actually you actually see is that if you look carefully, so these are the confocal images, that is a regular light microscopy images. And if you look carefully, you start seeing this zebra-like lines, which was not identifiable by, regular light microscopy. So many a times when I present my work, people used to ask me, what are those kind of things that has been identified by this kind of techniques that could not be identified, let's say by electron microscopy? Okay, or electron microscopy could not. I mean, this is one of the things that comes up. So it's one simple example. It's a collective body of work from a lot of people. I have just tried to just say, like, you can go and check these guys up, they are very good. But all what I want to say is that this was neither predicted by electron microscopy nor originally showed by electron microscopy. This was first identified by using super resolution microscopy. And this gives people still don't know why these structures actually form and their actual function. But the observation that these actually form, this kind of actin ring-like structures, have given us a different way to view cytoskeletal elements, or the elements that give shape to the cell. Okay. Now, yes. It's not a photo bleaching. It's like you are converting. If you take the Jablonski diagram, you have a ground state and a singlet state, right? So what you're trying to do is that singlet state is like not a stable state anyway, but it's an excited state. So what you try to do is that if you are trying to illuminate an ensemble of molecules, let's say you have n number of molecules, out of that, n1 goes to the excited state, but they all doesn't come at the same time. So there is an exponential decay kinetics that you have. So what the people what the stud does is that they try to illuminate like a few picoseconds or femtoseconds or maybe picoseconds after your original pulse has been given. Okay, or even the continuous it could be a continuous illumination. So then the annulus actually illuminates those in the like right outside. So those people who are still fluorescing, when the donut actually comes in, suddenly it goes back to the ground state. You understood? So it's not like bleaching. It's like forcing molecule to go from excited state to the ground state as quickly as possible.
So that is for the switching off the fluorophore in the donut outside the donut. What I'm asking is, if you have that laser putting up in a sample, that will bleach out the sample.
Oh yeah. Oh, you are. See, any illumination will bleach out the sample.
And if you want to switch off all the fluorophore outside that, then you have to put a lot of intensity in it.
But it is not in the same wavelength, right? So if you go back to the original image, so the original single photon excitation happens here. Understood? The stimulated emission happens after in the red shoulder of the emission spectrum. You understand? So the energy that you are giving to quench or for the stud, and the energy that you are going to stimulate and record fluorescence, these are different frequencies or different wavelengths. Is it clear?
And one, the shape of that donut shape, how small and how much the intensity is there? Like it's a proper zero intensity hitting, or
That, I mean, see, you know how the light works, right? It actually, it's a wave. So every light actually diffracts and interferes and so on. So it's very hard that you can actually have zero. You can have as minimum as possible, but it's very hard to keep zeros unless if you are getting close. If the annulus is coming smaller and smaller and smaller, that would mean that the bleed through into the center is also going to be larger and larger and larger, because a Gaussian beam is a beam with zero annulus, right? You understood? Clear? Any other questions? Yeah. So yeah, anyway, so I have put some, so basically, like, a good reference for starters, I have put this one. There are so many reviews that has come in super resolution, but this is actually a good one because it's actually not only talks about different types of super resolution, but also gives you about different imaging modalities, the configuration with which you have to image the sample. So I like this, so maybe it's a good one for you guys, I hope. Okay, so and now we actually move on to, so in the ensemble you try to illuminate a large subset of samples, then you try to quench the fluorescence outside, such that you try to get maximum information from the center of emission as much as possible. So in the case of single molecules, so this is again started, again happened. The original discovery started in the late 90s and early 2000. And by around 2006, 2007 time, the original proof of principles have come up on how we can use this. So how this works is very, in a way. So I told you that, you remember from my red blob, this is an example. So you have this green volume, where you have a lot of molecules that actually comes in. So what super resolution or single molecule or microscopy does is that so it tries to make sure that this molecules which is in volume, we start observing one by one. So not together, but somehow we induce a chemistry such that not all molecules are fluorescing at the same time. But we try to see whether we can somehow make sure the emission happens in a temporally separate manner. Okay, then what we do is that we somehow have a mathematical paradigm to calculate the center of emission, and then we try to create a new image by just plotting the center of emission of these events. I will explain to you in the next slides. Okay. So this kind of super resolution microscopy, which rely on single molecules, relies on the concept of sparsity of detection, which means like you don't want all molecules to fluoresce at the same time, but what you want is distinct subset which are very well separate fluoresce, and you can try to identify or analyze or try to estimate the center of emissions individually for these molecules. So basically this is a mathematically exhaustive process. Okay, so now how do they do that? So how do they create stochastic or random observation of single molecules? So you can actually try to do two ways. We will describe both ways. One of them is called stochastic labeling and the other one is called stochastic detection. In the stochastic labeling, what you try to do is that you try to, so you have, let's say, thousands and thousands of molecules that is there. So you try to make sure that you label one or two molecules at a time. So you try to take a ligand that's actually identifying the molecule, try to label it, and then you observe it. After you bleach only, after the fluorescence goes to the dark state only, the other molecules can come and bind to it. Okay, now it's exact. It's like like if you are in a crowded environment, if you are in a school, if teacher wants to, like, say, count each one of you, or take an attendance, and if everyone has to say the name, all of you cannot get up at the same time and say the name, right? So you individually start saying the name, and even if sometimes they are close together, teacher can somehow make out. but not when it exceeds a certain number. So it's similar principle applies here. So you want sparsity, you want like the identity of each molecules. And in this case, this is a stochastic labeling is almost trying to label one by one and trying to detect the create a picture of the density map of the structure that we are interested in. So now you have stochastic detection. So stochastic detection actually relies on like some of interesting chemical principle. In the previous one, it looked at the principles of association and dissociation. Here, it actually relies on the photophysical property of the molecules. So you have two ways in which you can create stochastic detection. That is, you can selectively activate molecules, and this is called optical highlighters or optically highlighting. That means you try to use one light to change the state of the molecule. And now you are trying to look at the new state with either the same light or with another light. So one of them is called the photo activation, and the other one is called as photo switching. Okay. In the photo activation, what it tries to do is that you have an excitation spectra and you suddenly shine with a low wavelength light, and it actually changes the number of photons or number of molecules or number of photons that are emitting before and after the illumination with the low wavelength light. So before, let's say if it had 10 photons, after you shine with a low wavelength light, it starts giving 100 or 1000 or 10,000. Okay. Now, in the case of photo switching, what could happen is that you have, like say, a molecule that has a very specific absorption emission spectra. What you do is that you shine a low wavelength light, so it switches both its absorption and emission spectra. That means if it was like trying to absorb a 488 nanometer wavelength and emitting at 510 or 509 nanometers, after it absorbs the light, it gets modified, the chemical gets modified and suddenly starts absorbing in 560 nanometer and emitting at 594. Okay, now how can we, what are the differences? So this is just a few examples of this molecule. So you can have, one shot process. For example, in some cases you shine light, it will be permanently modified, or you can also have reversible modifications. In the permanent modification, once you shine light, it has completely changed its state. In a reversible one, you can have these kind of switches. You can go from bright, dark, bright, dark, bright, dark states by constantly switching on and off the lights. But what's important is, what's interesting also is photo switching. For example, this is what you see. So I don't know if you look carefully, you see that, the system here has a green fluorescence, a green color. What I did is that I shined the same here at the tip of this. This is called, this is a spine. This is where you have the synapse inside your brain localized. What we try to do is that we shine it with a blue light. And once that means once it's shine, so the many molecules in this tip will get converted into red. Okay, now since this is a live cell, what you see here is that those molecules which are there, they are nowhere else, right? Those red molecules suddenly appeared over here, and they will diffuse out into the rest of the cell region. And this is, if you just observe only the red channel, this is what you see. So you will suddenly see a flash of light, and then it's gone. Now, if you look carefully, like say, this is what happens. So you can, at 0 millisecond, it's almost nothing. At 100 millisecond, we kind of illuminated at the tip. And by 1 second, it has gone and it has disappeared equally in the large volume of the cell, which means like this diffusion that is happening inside for molecules that do not have any specific, function is very fast. It's like as you put like a, a liquid, a small, very, very small drop of ink in water and just shake, it's just, spread out equally. Similar thing happens here. So now this happened because I gave a very high power of my blue light. But instead of that, if I am trying to give a very small amount of blue light and still keeping the imaging paradigm very similar. So this is my red, like say my green part of the protein. Sorry. Yeah. Now, when I convert this, you start, not all molecules get, how how will I say, converted at the same time, but you still see that few subset of molecules start getting converted, and you will see them as single molecules, right? So if you look carefully, let's look at some of them. For example, let's look at some molecules over here, this part. You will see that after a while it goes on and off, right? You will have some intensity, then it's gone, then it comes back. You understand? So if you now try to look at those kind of structures, you will see that the molecules are switching from on and off state. Understand? So you can now start looking. So with the same sample that you had before, you have arrived at the sparsity of detection. So rather than looking all molecules at the same time, you are actually seeing well isolated single molecule spread in a region of our interest. Now, what can you do with this? So we have attained our first goal of reaching single molecule. So we have somehow created a stochasticity, randomness in which the molecules are actually localized. Now what we need is that we need some mathematical program or some mathematical paradigm to accurately say where could be the center of these emissions. Okay, what we could do for that, for example, this is a single, like, a single molecular emission that you see. What you need here is that you need to calculate somehow center of this emission and let us know with what kind of accuracy or what kind of precision that you can calculate the centers. For example, like, you calculate everything, it's going to have an accuracy and precision, right? So similarly, you have a structure like this. You try to fit a Gaussian function. For example, you have a Gaussian function over here, and this red function that you see down, no, this in the middle is an error function. Basically, it tries to calculate how much error we have in fitting the center of such a Gaussian. Okay, now once we have this error, we can now create a new image. For example, if this was our old image, we can just represent our new image with just the center and the error. That's all. So how we can use this in real life? For example, this is a m that is that you have calculated. What we do here is that we are trying to create individual molecules that are lighting up in the field. Then at the same time that we are fitting the same molecule with the center and the error associated with it, and then reconstructing the final image. So this is a time-taking process, right? Because it's actually creating a mountain of data. Understand? So you will see, but one thing, whatever I say, one thing you can appreciate, that my ending image over here is way better than my starting. And you can also see that you see structures that was not originally observable in my beginning image. So which means are almost reaching where we should be. We create sparsity, we identify centers of emission of fluorophores, we estimate the center with precision, we have an idea of maximum likelihood idea of where the centroid is. Voila, you have almost reached the super resolution. Okay, now all said and done, how am I going to do it to the cells, right? So this is another example. This is called, we are trying to create optical highlighting through fluorescent states itself. So in this one, what you will see is that I put some chemicals into my cells which are fixed. And when I increase the intensity, you will start seeing that the cells or the structure, the continuous structure that you have already there, got bleached. And you will see that individual emission events are now occurring. And on the right side, we are reconstructing them in the real time. Okay, and which eventually ends up with very fine tubular structures. In one scale it was around 300. On the left side you had around 300 nanometer resolution, and here we have around 15 to 20 nanometer resolution. If you look carefully, if you look at structures over here or over here, this side, you can start resolving this individual fibrils with much better precision than you had for the diffraction limited image, which is on the left side. Now let's see if you are trying to look at the same thing. So this is my original image. This is a single molecule, and if you see here, you can fit this nice structures that will give you images of the better precision. Now the zooming won't give you pixels, but it start giving you structures inside what you want to see. So we will see whether it is true. So in later slides, but now we have reached two stages. So we have completed the first two, right? We need ability to create stochasticity. We need a mathematical power of maths to recreate the centers. Now all you need is a good microscope, which you have mostly seen in Partho's lab. So I will skip that part. Okay. So now if you are trying to look, for example, this is, I'll just give you a very small example. This is an endogenous image of NAPP or amyloid precursor. This is a protein very much involved in Alzheimer's disease. I wouldn't go into the details. So if you look through a regular light microscope, you see a staining pattern like this, which seems like it is heterogeneous, but it looks more or like continuous, right? But now if you are going for the same cell, when you are imaged by super resolution, the things change. It's not continuous anymore. You start seeing very small islands of molecular clusters. And each of these islands are around, 50 to 100 nanometers in diameter. That means it is at least 2 to 3 orders, 2 to 3 times smaller than the diffraction limit that you can get with the regular microscope. Okay. So now, if you look carefully, again, I'm just trying to zoom it in so that you can appreciate this. So this is a wide field image that you see, and these are the super resolution images. You can nicely, so if you look at these structures, you can nicely see. So while it was a big blur over this side, here you can see this is actually created by 3 separate domains. Okay. Now, we will just try to go so far, till this much time, we have actually tried to use the cameras that are integrating signals. So what do you mean by integrating signals? When you have a mobile phone, when you try to record a camera, what it tries to do is that in X amount of time, it collects all the photons and create an image. Understood? So basically, if you are trying to, let's say you are trying to image such a mobile, I think it's around 20 to 30 millisecond or time interval it records thing, you will see everything in, right? Every all the integrated photons are coming to its detector, and an image is thus formed. But now think about a detector that can actually differentiate things. How would you do that? So for example, what does it mean by differentiating these events? So now I am trying to take an image of this room. Okay. So all the people who are sitting here or not moving the position, I won't detect in the next frame. I'm only going to detect those people who are moving out. Understand? Because when you differentiate, constant things, it actually becomes zero. Understand? So if I want to look at a room, a dark room, okay, I'm just trying to keep this camera and I'm trying to switch on the light. So when I switched on the light, when I switched it on, I get an increase in the brightness in the room, right? So I calculate it as an event. Now, while the light is on, there is not much difference in the intensity of the light that's coming out. So you will not detect any events anymore. Now, once you switch it off, it will go down. Understand? But if you are trying at the same time, if you are trying to use the same thing, like the regular conventional detectors to image such an event, when you do that, when you switch on, you will see the dark room, nothing. When you switch on the light, you will see once it is switched on, and then everything as it's integrate. And once you switch off, you don't see it anymore. But the advantage for here in the kind of neuromorphic is that you not only record on events, but you also have a potential to record off events. Understood? So now I have to thank these guys. They have been tremendous. So this paper was led by Rohit and ably supported by both Mini and Nivi. And so we have actually tried. So till this much time, we were also trying to think about the ideas to create sparsity and using chemistry. Now, here we are trying to, because we can start differentiating the signals, we are trying to reach a way to create sparsity at the detector level. As simple as that. Now we will see how we could go. We need to create something that will actually mimic our eye. Because if you look at our eye, we have a good sensitivity for detecting fast events as well as stable events. So if you want to concentrate on events that are moving, we can concentrate there. If we have to focus on stable things, we can also concentrate over there. So we try to identify, or we try to rely on how the eye detects the moving structures and try to create detectors which are very similar to that. So what it does is that, so these are the structure that you have for the eye, and here we try to create a set of electronics that would actually create this thing. I wouldn't go deeper, but what I want to bring your attention is this graph on here. So what it does is that when the intensity is actually increasing, you will start seeing, that it will be detected as on events. Now the problem here that you need to remember is that, you cannot record something that is not there, something that is decreasing. All you have left is like, is a grayscales to detect, right? So what you try to do is that you try to go away from the classical grayscales and you start creating something called as polarities. So that means when the light is getting on, you say that it has a positive polarity, which means like it has a spike which is going towards an increase. That is the rate of change is towards increase. When you have an off events, the rate of change is towards decrease. Okay, now we can also see this is the same thing that happens. So for example, it can detect, so blacks are on events, that means the where the movement happens. So for example, if you just wave your hand over the camera, blacks are where you have the movements happen, and red is where it was previously there. So that means you have a very good system right now, while the EMCCDs or SCMOS or conventional cameras will give you just on events. For the same event, for the same molecules, now we are getting two different processes, one on and one off. It's like a coin switch, right? I mean, you have both the head and tails in with one detector. You can, and you have a better probability now for detecting the particles, and that's what we will go in. So this is what happens. So if I am trying to take an EM, I think I have to hurry. Okay. So this is on the top you have an EM detection, and on the bottom you have a neuromorphic camera detection. You will see that here you will see an increase, a decrease, an increase, a decrease. That means I alternatively illuminate with high intensity and a low intensity. While if you look in the neuromorphic, what you will see here is that you will see that green and red. That means it will either detect, those pixels will detect. Green means an increase in signal, red means a decrease in signal. Okay, so it is trying to detect it as polarities of change. Now what happens is that not only that so if we can separate out these events from the same time stream. You can just have pixels that are responding to only on events and the pixels that are responding only to off events. Now this is beautiful because you can see that in the on events, when the molecules are now going to off state, it records almost nothing. Understand? While for the off events, when the molecules are going to on state, it records nothing. That means same molecule, now you can have, rather than having one, you can have twice. Okay, and you can start trying to go away from the grayscales and start looking at the polarity scales that you can. Okay, now you look at it. So now the second thing that is there is that, when you integrate signals, you always try to give a time window. Understand? So you say that, okay, I am going to collect all the signals that are coming in 10 millisecond time window, or 20 millisecond time window, or 50 millisecond time window. But what this kind of detectors does is that it do not need a time window. So it can actually detect events, and you can bin the time as much as you want, however you want post acquisition. Okay, so normally you can do it for EMCCDs or conventional cameras too, but only after, but the averaging effect starts taking its place. You are going to average between two frames. Like say I collected 50 millisecond acquisition, and now if I want to convert it into a 100 millisecond acquisition, I am going to average two frames. Here the averaging effect is almost on, because it's actually recording events. Okay, and it's only recording both only on and off. So now if you look, this is an event. So for example, 100, what we tried is that in the beginning of the 100 millisecond, I just gave a small laser pulse to switch it on, and after this, it switched off. That means once the laser hits, so if I go here, once the laser is at a high power, it's staying constant. Understood? And once it is coming to the low power, it's staying constant in that time window. So what eventually you happen is that once the laser is increased, the signal output is constant, or decrease, the signal output is constant. Now we try to take the same event and started trying to divide it into different temporal windows. For example, this is a 100 millisecond event. So you start dividing 100 millisecond into 250 millisecond. You will see that only in the first frame you can see the green. In the second frame, it's almost very less, which indicates that the rate of change was detected in the first 50 millisecond. Okay, and now if you divide it to 25 millisecond, you see it's in the first 2 frames. Now if you go and divide it into 10, you will see that it is in the first, like say 2-3 frames, indicating that it is actually recording the events rather than just integrating them at will. Okay, now it's up to us. How much bins we want, we can give it after acquisition, because this is the same data. We haven't done anything. We have taken the same data, we have split them in time. That's all. Okay, now what we see, once we take the raw data, what will happen is here is that yes. So this is what happens. So in a 100 millisecond window, so we are constantly giving between on and off. Every green event is an increase in intensity, and a red event is now a decrease in intensity. Now it's very simple, because you can remember the classical way. So you can actually segment them out, create Gaussian maps, for green and red separately, and then go ahead and calculate the centroids. Understood? Now I think so we can, for the same molecule, now we have 2 centroids, one in the on and the other in the off. Okay, we go further. This is how it happens. So this is the green. So these are the thing. So this is a segmented molecule. This is the localized. And for green, this is for the on events localization, off event localization. So if you overlay them, you will see that they're almost in the same place. So you have 2 kinds of probabilities, or 2 kinds of principles of detection, but they are spatially localized to the same compartment. Now what we did is that if I am trying to take an on event, okay, I am only going to get the signal from one of this, right? So now I have both the information, how I can combine to improve the precision with which we can localize the molecules. That's what we did. But before that, I just want to show you the graphs of the temporal events, but now it's not, only it's showing that these are true events. So you are not going to get flat, but you are going to get triangular kind of waves, not like, but that's okay. I'll just skip and go. This is the most important part here. So this is the regular diffraction limited image that you have. So on the on and off. Now here, what we have done is that we have fit the centroid. But in these two, what we tried is that we tried to subtract the probability function of on from off. And in here, we tried to multiply the probability function of on with off. Okay, now and what you see on the top is the raw functions, raw data that you get. And what you get in the bottom is that you get the what happens after fitting a Gaussian to it. It means it gives you a fitted data. Okay, if you look carefully, you can see that, if you look in the right side panels, like if you look over here, that gives you a better precision, because when the data here was spread across many pixels, in this it is almost spread only on 1 pixel. Like if you look carefully, like every time if you look at the right side panels or these panels, you see that it is way better than that we have for on and off alone. Okay, so we look carefully again. So this is again the probability density function of calculating the centroid only for the on process. This is the error in Gaussian. Okay, this is only for the off process. But if you are subtracting things, you get, like this. But if you are multiplying this, you get a symmetric, very sharp localization. So the same thing, these are for multiple molecules. Every time you do this processing, you combine the information from the on and the off, you are actually improving the limits, or we are improving the precision with which you can calculate the center of these molecules. Okay, now what we do, so we try to mathematically see whether we see an improvement. I don't know whether you can see this. So if you look carefully for the on and off events, it's the circle is slightly shifted. So this gives you around, let's say, around 10 to 20 nanometers of in this range, the the X and Y. But if you are trying to look at the subtracted and the multiplied images, it's going to give almost, the deviation that you have here is from 4 to 11, while it is here, it is from 16 to 22. While here it is 10 to 15, and here, again, both of these are 16. So which means that you have an increase, you have a better way to calculate the centaurs. And you have to remember that this is the current detector, conventional detector technology is way advanced. So that means there are amplification factors. That means if you detect, you can 100 times amplify the signal, while we are getting this with no amplification factor. If we are getting a detector which is 20 to 30% as sensitive as our conventional detectors, we are going to reach almost 1 to 5 nanometer scales of detection. That means we should be able to see substructures in individual molecules easily. Okay. Now we come back and we try to look again at the same thing. You will see that, in the regular case, in the regular on-off processes, you will see it is higher. But for both the subtraction and multiplication, it is significant and it is actually lower. This indicates that, the two things. One is that you can combine on and off information to beat even the limits of diffraction that people have predicted 10-20 years back. Second is that now I have told you first that it is not only about localizing something, it's also about trying to understand from when and how they come in, right? So you need to also get an idea about how they move. So this is an example. So this is again a protein which is expressing on a cell surface. And what you are going to see here, so this, what you see here, like Bangalore traffic, is like, all the molecules moving on the surface of the cell. So in all possible directions. Now, if you look carefully, so when I fit the centroids of this thing, so this was my original image, I improve the how will I say, the precision with it. I improve the thing, and you can see substructures. And these are the paths each of the molecules have taken. So now we are looking at the individual molecules, we are looking at their properties, and we can arrive, if we want, we can keep them single, or we can accumulate all of their data and reach ensemble. So now what will we do? So this is an example of such a thing. So you will see that everywhere the molecules is moving very nicely. But if you look at these substructures that you have for these dark structures, where you have high density of localization, the question is whether this is a point which is actually passed by many molecules, like a junction, or do the molecules actually interact and stay over there? It's like when you go to a party, you can go to, many people run across, like, Pepsi counter, chicken masala counters, and so on. So, and some of the crowded places that you have, many people, they won't buy, but they just want to see what is happening. Understand? So, but those people won't stay there. They will just pass through. Okay. Similarly, the molecules are also like that. There are molecules will pass through, and there are molecules that will interact intimately with its microenvironment. And so the question is how we do that. For example, if you look here, so it is taking large steps, if you look at large steps till it reach here, and then suddenly it takes smaller steps. Understood? So how can we identify this difference in the microenvironments? By looking at how fast the molecules will move, how fast they interact with like a small nanoscale compartments. So this is what we did. For that, we try to relay something called as mean square diffusion. But this is like conceptually, again, it's very simple. So this is the trajectory. For example, in position t is equal to 1, it was here. T is equal to 2, the molecule was here. T is equal to 3, it was here. So what people try to do is that it actually tries to calculate first the, I will just, where is my laser? Yeah. So people try to calculate the mean square distance between first points. So for example, tries to calculate the mean square distance from the first points and then till the end of the trajectory, and that will give you the first port. Now, if you are trying to do it with every subsequent, now it's going to give my second point. Okay, like that we can do it till the trajectory depletes, and it will have only one point, and it will result in something called as like a mean square diffusion curve. Okay, now the beauty of mean square diffusion curve is in how you understand this. That I'll go into the next slide. So this is a trajectory. If something is moving unobstructed, so for example, if the molecules are very random movement, not interacting, it will almost show a linear curve for the. That means how much of your all points are going to have similar MS. You understand? And now, if it is like a directed transport, for example, if it is taking a destined path from one to other, you will have one side, it will have X or Y more than the other one, right? Deviations in the space. So you are going to have this kind of curve where it turns upwards. These are called directed mode. While those molecules that are increasingly interacting with the microenvironment, they get confined. So the curve starts coming down. Now you can start looking like hundreds of individual different trajectories and start making out how how individually these molecules interact. Now this is very powerful because you can actually look at one small compartment, take n number of molecules and say that which interacted where. This is exactly like telling you how your behavior changes when you're at home, when you're at school, when you're with friends, and when you're with your boyfriend, girlfriend, or a spouse. So you are going similarly, you are the same person, but where your spatial location is and the time is, you change. Similarly, the molecules too. Okay. Now, this is exactly what happens. So you can go ahead and start trying to confine properties to these individual trajectories to see whether this is occurring as a result of confinement or any other properties at the level of individual molecules. Now we go back again, sorry, we try to see, we can still improve because we have on and off processes for the neuromorphic cameras, right? So we can try to look at the on and off processes, and here we can see, because they are recording very fast, this is a diffusive molecule, so the green is on, red is off. That means whenever the green molecules move, the red shows that it was the previous position the green was in. Understood? Now we can go ahead, we can try to fit the centroids for each of this. So, and create the segmentation. So you can see now individually how these molecules actually go, because these are the same molecule, they should have same kind of kinetics, both on and off process. Now we go ahead further, we can look at individually these trajectories, we can try to localize the maps and things, so you will have everything. I am showing an example for one trajectory, but eventually you are going to be left with 10, 100,000, 200,000 of trajectories. So that's what I say, it's a mathematically exhaustive step, because iteratively it has to always go back and calculate its positions. Okay. And now you go back and try to look at how individual trajectories are actually made. Okay. Now we go back, because we have neuromorphic camera can give us both position as well as we can split events in any kind of time. We can actually go back and look how one particle moved in different temporal windows. Okay, I'll give an example again. For example, like you are in a football ground and you're trying to walk in the football ground randomly. I'm trying to take a picture of you every 1 minute. Understand, and connect your positions. You will see that you will have larger distances, much more finer. But as you decrease it to, let's say, around 1 second. Understood? So you are going to have every step probably is going to get recorded. So it's going to have more finer structures than you have seen in your large windows. That's exactly what you see. For example, here the same neuromorphic data that we had without binning, we had actually seen, this is at 100 millisecond. For example, these data on the left are 100 millisecond. That means we took an image, we tried to accumulate data every 100 millisecond. But as you go to 10, just an order of 1, you will see that it is the same molecule, it is the same path, but you will see more refined structures coming in. Understand? That creates a fractalization of trajectories, which is obviously seen in diffusive kinetics. Understand? So that means neuromorphic camera can not only give you a better pointing accuracy, but it can also give you a better temporal precision and can identify, look at the same molecule, same trajectory in different temporal windows, how it has interacted. Okay, and this is very interesting because we try to do a simple test, because if I am trying to mix something in water, whether the concentration is high or low, whether the temporal windows are high or small, it should have same rate of diffusion. Understand? So if I am trying to measure how much that you travel from Bangalore to Mysore, whether I am measuring your speed in every, like say 10 minutes or every 1 minute, it should give you the same speed. Understand? If you're, so this is the same thing. So if you look at here, so that's what we see. The center of the mean square diffusion, you can see that it's almost close. The curves really overlap. And you see that here also you see a very good overlap. But once I start going to conventional detectors, and unfortunately I forgot to put the data over here, at larger time temporal windows, it starts deviating because it's going to have the averaging effect. Understood? So now, so far, I think at this point, I think I have eaten your brains. So I think I'll kind of try to stop. So thing that we have gone through today is that maybe you might have got a rough idea about what does it mean by single molecule localization microscopy. What does it mean by using conventional cameras to generate single molecule localization microscopy? How you can study localization and trafficking at nanoscale and at real time. Understood? How we can use non-conventional, non-linear detectors like neuromorphic to bin different information to improve it further. Understand? And how you can use on-off processes to study fractalized diffusion. Now, these things have tremendous applications, in cell biology, chemistry, and all, because every processes that you have is finally defined by stochasticity. So the more information that you can get from individual pools of molecule, the more we are able to describe or predict how the system will evolve. Okay, like reaction diffusion kinetics in chemistry. Every reactant, when it comes and collide, may not result in a product. Now, there is always a probability that a product can be formed. It can either be at intermediate states, go back to reactant, or it can form products. Similarly, similar to biology also. The more you are able to understand the real-time heterogeneity of these interactions and the molecular trafficking organization, the more we can appreciate how biology is organized at its finest scale. And at this point, I am extremely, so this is all the faculties at Center for Neuroscience, not all, but large of them. But for this work, I have to thank a lot of people, who have helped, in different aspects. And, particularly to the funding agencies who have given us money, and the funding agencies who haven't given us money, because that has actually helped us to prove them wrong, that it actually does it. And also many other people who are, visibly thanked here, and also those who have been supporting, like the supporting faculty, supporting staff at CNS, IAC, and all the facilities that we have used. Last but not least, thank you for your attention.
So I thank Deepak. This talk was very absorbing, and now this localization microscopy, and the applications. As I said in one of the when we were meeting in the morning, that localization microscopy is not only about biology. It can go into chemistry. It can go into engineering in future. So it can just expand. Okay, so this is what I think Deepak has shown. A indeed very absorbing talk, and one of the finest talk, I would say. And you can look at all the talks that we have had, but one of the finest talks. So I thank Deepak once again, and we'll move on to lunch and other things, so that that's the most important. Thank you.